Hello, Chem 30. This is our third lesson in the thermochemistry unit. This is calculating enthalpy change. In this lesson, we are going to learn how to calculate changes in kinetic and potential energy and move forward with 6 examples. Kinetic energy changes are measured by a temperature change and calculated using the following equation. Delta H, or Q, equals mc delta T. Heat, or Q, is measured in joules and is the total energy transferred from a hotter system to a colder system through contact. Enthalpy change, or delta H, is the same as Q, but is typically measured in kilojoules. Mass is measured in grams. Specific heat capacity, or C, is measured in joules divided by grams times degrees Celsius. It is important to note that specific heat capacity will always be a positive value. Also, mass will always be a positive value. Finally, change in temperature is measured in degrees Celsius and is the final temperature minus the initial. It is important to note that when looking at the units involved in the calculation of mc delta T, your answer will always come out in joules, and that is because of the units in specific heat capacity. If you are looking for a value in kilojoules, you will then have to divide your calculation by 1000. Potential energy changes occur when bonds change, which would be intramolecular forces in a reaction, or when there is a state change, which would be intermolecular forces, and this can be calculated using the formula delta H equals NH. Enthalpy change, or delta H, is the change in energy of a process and is measured in kilojoules. N is moles of a substance, which is measured in moles. It is important to note that N will always be a positive value. And finally, molar enthalpy, or H, is measured in kilojoules per mole, which is a ratio between the energy and the moles of a species in a chemical reaction. It is important to note that molar enthalpy is specific for each species in every reaction. Example number 1. 115.24 grams of isopropyl alcohol at 20.1 degrees Celsius was mixed with 56.31 grams of water at 50.3 degrees Celsius. After thermal equilibrium was reached, the temperature of the mixture was 36.5 degrees Celsius. What was the energy lost by the water in kilojoules? Pause this video and attempt this example. In example number 1, it is important to note that there is a temperature change. Therefore, this has to be a kinetic energy change. We will be using the equation Q equals mc delta T. We are concerned with the energy lost by the water. Therefore, we need the mc delta T values for water. We are taking the 56.31 grams of water and timesing it by the specific heat capacity of water. This value can be found in your Chemistry 30 data booklet. We will then times it by the temperature change of the water. That is the final temperature of the water, 36.5, minus the initial temperature of the water, which was 50.3 degrees Celsius. This calculation gives us negative 3,255.956 joules. The question then asks us to find the energy lost by the water in kilojoules. We will then have to divide that value by 1,000, which would give us negative 3.26 kilojoules. That is 3 significant digits as our end answer, because that was the lowest going in to the calculation. Example number 2. The molar heat of solution for sodium hydroxide is negative 44.6 kilojoules per mole. If 25.0 grams of sodium hydroxide is dissolved in water in a calorimeter, what is the heat released inside the calorimeter? Pause the video and attempt this example. In example number 2, we are dissolving an ionic compound in water. Therefore, we are going to break apart the intramolecular forces, which will be a bond change. Also, there is no temperature change noted in this example. Therefore, this will be a potential energy change, and we will use the equation delta H equals NH. We can see in this equation that we are dissociating sodium hydroxide into water, forming its ions. This is, again, a bond change. We do need the molar mass of sodium hydroxide, which is 40.00 grams per mole. Our equation, delta H equals NH. We can then put our values in for N. To find the moles of sodium hydroxide, we will take the 25.0 grams divided by its molar mass. This value will give us the moles of sodium hydroxide. We will then times it by the molar heat of solution for sodium hydroxide, or the H value. That then gives us a delta H value of negative 27.9 kilojoules. That is 3 significant digits, because we are starting with 3 significant digits in our calculation. Example number 3. If negative 44.7 kilojoules of energy is released when 1.65 grams of ethanol is burned in a calorimeter, what is the molar enthalpy of combustion for ethanol? Pause this video and attempt this example. In example number 3, we are burning ethanol. This is a combustion reaction, therefore, this is a potential energy change. Also, the question asks us to find the molar enthalpy of combustion for ethanol. This is an H value. Therefore, the only equation with an H value is delta H equals NH. We are going to rearrange the equation to solve for H, which is equal to delta H divided by N. We do need the molar mass of ethanol, which is 44.06 grams per mole. We can then take our delta H, negative 44.7 kilojoules, and divide it by the moles of ethanol. We are finding the moles of ethanol by taking the 1.65 grams divided by its molar mass, 44.06 grams. That gives us an H value of negative 1.19 times 10 to the third kilojoules per mole. Again, 3 significant digits because that was the lowest value of significant digits that we started the calculation. Example number 4. 115.24 grams of isopropyl alcohol at 20.1 degrees Celsius was mixed with 56.31 grams of water at 50.3 degrees Celsius. After thermal equilibrium was reached, the temperature of the mixture was 36.5 degrees Celsius. What is the specific heat capacity of the alcohol if the water lost 3.26 kilojoules of energy? Pause the video and attempt this example. In example number 4, there is a temperature change. Therefore, this is a kinetic energy change. We will be using the equation Q equals mc delta T. The question asks us for the specific heat capacity of alcohol. Therefore, we are looking for a C value, and we have to use the values of m delta T and Q, which are corresponding to the alcohol. We have to assume if the water lost 3.26 kilojoules of energy, then the alcohol had to have gained that exact same amount of energy. We can then rearrange Q equals mc delta T to get C equals Q divided by m delta T. Again, we do need the values corresponding to isopropyl alcohol. We will then take 3,216 joules, which was originally the 3.26 kilojoules, and divide it by the mass of isopropyl alcohol, 115.24 grams, times by the temperature change of isopropyl alcohol, which is 36.5 degrees Celsius minus 20.1 degrees Celsius. That then gives us a specific heat capacity of isopropyl alcohol of 1.72 joules divided by grams times degrees Celsius. Our answer will have 3 significant digits because that was the lowest significant digits going into the calculation. Example number 5. You are given 2 metal samples at 20 degrees Celsius, 50 grams of tin and 50 grams of copper. Which metal would heat up to 100 degrees Celsius first? Pause the video and attempt this example. Example number 5 corresponds to the specific heat capacity of each metal. The specific heat capacity of tin is 0.227, and the specific heat capacity of copper is 0.385. Comparing these two values, it is clear to see that it requires less energy to convert 1 gram of tin 1 degree Celsius. Therefore, if we applied the same amount of energy to both metals, tin would heat up faster to 100 degrees Celsius because it would require less energy. Example number 6. Using the equation, determine the amount of energy released by the combustion of 100 grams of C2H2 in megajoules. Pause the video and attempt this example. Example number 6 involves a combustion reaction, which we can see in the chemical equation below. Therefore, this will be a potential energy change, and we will be using the equation delta H equals NH. We are given a gram value in the question, which we can convert to moles. Determine the amount of energy released refers to delta H. The problem is that we are not given an H value in the question. We can use the chemical equation and take the energy provided and divide it by the coefficient in front of C2H2. This will give us the molar enthalpy of combustion for C2H2 in this chemical reaction. Note how the value is negative, 1,255.5 kilojoules per mole. That's because the energy was provided on the product side of the chemical equation, representing that this is an exothermic reaction and we are losing energy. We do need the molar mass of C2H2, which is 26.04 grams per mole. Again, we are going to use the equation delta H equals NH, and we put our values in. We will take the 100 grams divided by the molar mass of C2H2 to get our answer in moles, and times it by the H value, negative 1,255.5 kilojoules per mole. That will then give us a delta H value of negative 4,821.42 kilojoules. We then have to divide by 1,000 to get our answer in megajoules. Our answer is negative 4.82 megajoules. That is 3 significant digits in our answer because we started our calculation with 3 significant digits. The many H values. At this point in time, we have worked with delta H and H. Enthalpy change, delta H, in an equation only represents the energy change for the coefficient mole values. Therefore, in this chemical equation, we will release negative 2,043.9 kilojoules when we combust 1 mole of C2H8 with 5 moles of O2 and forming 3 moles of CO2 and 4 moles of H2O gas. Delta H must be calculated using delta H equals NH when other mole values are used. For example, 100 grams of C2H8. That is because 100 grams actually equals 3.33 moles, not 1 mole. Molar enthalpy, H, can be calculated from a balanced chemical equation. For example, if we take the delta H value in the chemical equation above and divide it by 4 moles, we will get the molar enthalpy of H2O in this specific chemical reaction. H can also be calculated using delta H equals NH. And finally, H can be taken from the Chemistry 30 data booklet, but only if the reaction is a formation reaction, or the exact opposite, which would be a decomposition reaction.
Moving forward, we will look at calorimetry and energy change.